Quantum superposition. Quantum superposition is one of the most fascinating and counterintuitive concepts in physics. It tells us that, at a fundamental level, particles like electrons or photons can exist in multiple states or positions simultaneously until they are observed or measured. To make this idea more relatable, let's use an analogy and a few examples from the world around us. Imagine flipping a coin. In everyday experience, the coin is either heads or tails once it lands. However, in the quantum world, a flipped coin doesn't land on heads or tails immediately. Instead, it exists in a strange limbo, where it is simultaneously both heads and tails. This is quantum superposition. It is only when you look at the coin, analogous to measuring the quantum system, that it decides on one outcome. This strange behavior arises because particles at the quantum level don't behave like solid objects in our classical world. Instead, they act like waves of probability, existing in all possible states at once. One classic illustration of superposition is Schrödinger's cat, a thought experiment proposed by physicist Erwin Schrödinger. In this scenario, a cat is placed in a sealed box with a mechanism that has a 50% chance of releasing poison based on the decay of a radioactive atom. According to quantum mechanics, until someone opens the box to observe the cat, the system exists in a superposition of both cat alive and cat dead. The act of observation collapses this superposition into one definite state, either alive or dead. While Schrödinger used this example to highlight the apparent absurdity of applying quantum rules to everyday objects, it underscores how superposition works at a fundamental level. In practical terms, superposition is not something we experience directly in our daily lives because macroscopic objects like cats, coins, or ourselves are not governed by quantum behavior in the same way as subatomic particles. This is due to a process called decoherence, where interactions with the environment destroy the superposition, leaving the object in a single, definite state. However, superposition has very real applications in technology, particularly in quantum computing. Unlike classical computers, which use bits to represent information as either a 0 or a 1, quantum computers use quantum bits, or qubits. A qubit can exist in a superposition of both 0 and 1 at the same time. This property allows quantum computers to perform certain calculations exponentially faster than classical ones by exploring multiple solutions simultaneously. For example, consider searching through a massive database. A classical computer would need to check each entry one at a time, while a quantum computer, thanks to superposition, could evaluate multiple entries simultaneously, dramatically speeding up the process. This potential has led to groundbreaking research in areas like cryptography, optimization, and drug discovery. Another real-world example of superposition comes from quantum experiments, like the famous double-slit experiment. When a beam of light or electrons is directed at a barrier with two slits and no observation is made, the particles exhibit an interference pattern, as if they pass through both slits simultaneously, behaving like waves. However, when a detector is placed to observe which slit the particle passes through, the interference pattern disappears, and the particles behave like tiny solid objects. This experiment shows how superposition works and how observation affects it. While superposition may seem abstract, it reveals the strange and fascinating nature of reality at its smallest scales. It challenges our intuitive understanding of how the world works and opens the door to revolutionary technologies that could reshape our future. By studying superposition and its implications, we gain insight into the hidden rules that govern the universe, providing a deeper appreciation for the complexity and wonder of the natural world. Time dilation. The concept of time dilation, rooted in Einstein's theory of relativity, challenges our everyday understanding of time. In simple terms, it suggests that time does not flow uniformly for everyone. Instead, it can stretch or compress depending on an observer's speed or proximity to a massive gravitational field. This phenomenon is not just a theoretical curiosity, but has practical implications, affecting technologies like GPS and altering our perception of reality. To understand time dilation, imagine two observers, one moving at a high speed, say aboard a spaceship traveling close to the speed of light, and the other stationary on Earth. According to Einstein's theory of special relativity, time slows down for the moving observer relative to the stationary one. If the spaceship traveler carries a clock, it will tick more slowly than a clock on Earth. This effect becomes increasingly significant, as the speed of the spaceship approaches the speed of light. An example often used to illustrate this is the twin paradox. Imagine a pair of twins, one of whom embarks on a high-speed journey through space while the other stays on Earth. Upon returning, the traveling twin will have aged less than the twin who stayed behind. This isn't a trick of perception, it's a measurable and real consequence of the universe's structure, confirmed through experiments with particles and atomic clocks. This effect isn't limited to high speeds. Time dilation also occurs due to gravity, as described by Einstein's general relativity. A stronger gravitational field slows time relative to weaker fields. For example, time moves slightly faster at the top of a tall skyscraper than at its base, because the top is farther from Earth's gravitational center. While this difference is minuscule, it becomes much more pronounced near extremely dense objects like black holes. In the movie Interstellar, this concept is dramatized when astronauts orbiting a massive black hole experience time far more slowly than people on Earth. A few hours near the black hole equates to years passing back home. You might wonder if time dilation has any relevance to your daily life. Surprisingly, it does. Consider the GPS satellites orbiting Earth. These satellites experience two kinds of time dilation, one due to their high speed, special relativity, and another due to their distance from Earth's gravitational field, general relativity. Their onboard clocks tick slightly faster due to weaker gravity and slower due to high speed compared to clocks on Earth. Engineers account for these differences to ensure GPS signals provide accurate location data. Without correcting for time dilation, GPS systems would accumulate errors of several kilometers each day. Time dilation also plays a role in high-energy physics. For instance, particles called muons, created when cosmic rays hit Earth's atmosphere, decay in microseconds. However, because these particles move at near light speed, time dilation allows them to travel much farther than expected before decaying, enabling scientists to study them in detail. The implications of time dilation extend beyond practical applications. It forces us to reconsider the very nature of time. Wave-particle duality. Wave-particle duality is one of the most fascinating and perplexing concepts in physics. It suggests that entities such as light and matter exhibit behaviors characteristic of both waves and particles, depending on how they are observed or measured. To understand this idea in an everyday context, let's explore its origins, implications, and relatable examples. The concept arose in the early 20th century during the development of quantum mechanics. Scientists observed that light sometimes behaves like a wave, as seen in phenomena like diffraction and interference, and sometimes like a particle, as demonstrated in the photoelectric effect. Similarly, matter, like electrons and atoms, was also found to exhibit dual behaviors. This duality seems counterintuitive because, in our everyday experiences, waves and particles are distinct. For instance, water waves spread out and interfere with each other, whereas particles, like grains of sand, occupy discrete positions and do not blend in the same way. However, at the microscopic scale of photons, light particles, or electrons, this clear distinction between waves and particles breaks down. A helpful analogy is thinking of a coin that can either show heads or tails when flipped, but never both at the same time. Wave-particle duality is like having a magical coin that can exhibit traits of being heads and tails simultaneously, depending on how you observe it. Take light as an example. When you shine a flashlight into a room, you likely think of light as a wave spreading through the air. This wave-like behavior explains why light bends around corners, diffraction, or forms colorful patterns on soap bubbles due to interference. However, if you place a solar panel in the same room, light behaves like tiny particles called photons, each transferring energy to generate electricity in the panel. The context of the observation determines which behavior, wave or particle, manifests. Similarly, electrons also exhibit duality. Consider the famous double-slit experiment. When electrons are fired at a screen with two slits, and no one observes their path, they form an interference pattern on a detector screen, indicating wave behavior. Astonishingly, if you observe which slit the electrons pass through, the interference pattern disappears, and the electrons behave like particles. This experiment underscores that the act of measurement plays a critical role in determining the observed behavior. Wave-particle duality has practical implications in technologies we encounter daily. Devices like cameras, solar panels, and even the screens on your smartphone rely on an understanding of this duality. For instance, the photoelectric effect, which demonstrates light's particle-like properties, is the principle behind solar cells. Similarly, electron microscopes, which provide images of objects at incredibly small scales, exploit the wave-like nature of electrons to achieve their remarkable resolution. This duality also governs the behavior of matter at the atomic and subatomic levels, which forms the basis of quantum mechanics. It explains why atoms have specific energy levels and why chemical bonds form in the way they do. Without wave-particle duality, the periodic table, chemistry, and much of the modern world would not make sense. Wave-particle duality challenges our intuitive understanding of the world, suggesting that nature operates differently on the microscopic scale. It teaches us that reality isn't always as it appears, and that observing a phenomenon can alter its behavior. By embracing this duality, scientists have developed groundbreaking technologies that shape our lives, from lasers to quantum computers. While the concept spacetime is one of the most fascinating concepts in physics, providing a fundamental framework for understanding how the universe operates. To explain it in everyday terms, we must first move away from the idea that space and time are separate entities. Traditionally, we think of space as the three-dimensional arena where all events occur, and time as a separate, one-dimensional flow that marches ever forward. However, Einstein's theory of relativity combined these into a unified, four-dimensional fabric called spacetime. Imagine spacetime as a flexible, stretchy sheet, like a trampoline. Objects with mass, such as stars and planets, cause this sheet to warp or curve. This curvature isn't just an abstract idea. It's what we perceive as gravity. For instance, when you place a heavy ball on a trampoline, it creates a dip in the surface. Smaller objects, like marbles, placed near the ball, will naturally roll toward it, not because the ball is pulling them directly, but because the trampoline's shape has changed. Similarly, in spacetime, the sun warps the space around it, causing Earth to orbit it, much like the marble rolling along the curved surface. This understanding of spacetime changes how we think about gravity. Instead of being a mysterious force acting at a distance, as Newton described it, gravity is simply the result of the warping of spacetime by mass. The more massive an object is, the greater its curvature, and the stronger its gravitational pull. Black holes, for example, are regions where spacetime is so intensely curved that not even light can escape. Now, let's think about how this concept applies to time. Time, in Einstein's model, doesn't tick uniformly everywhere in the universe. It flows differently depending on the curvature of spacetime. This phenomenon, known as time dilation, can be experienced in extreme situations, though its effects are usually too small to notice in everyday life. For example, astronauts aboard the International Space Station age slightly slower than people on Earth because they're farther from the planet's massive gravitational field, where spacetime is less curved. This difference is minuscule, but measurable with precise atomic clocks. A more relatable example of spacetime's effects on time comes from GPS technology, which relies on satellites orbiting Earth. These satellites experience less gravitational pull and move faster than objects on the ground. Both factors alter the rate at which their onboard clocks tick compared to clocks on Earth. Engineers must account for these differences, calculated using Einstein's equations, when designing GPS systems. Without these corrections, your smartphone's navigation system would quickly become inaccurate. Spacetime also explains why objects traveling at speeds close to the speed of light experience time differently. If you could travel on a spaceship moving near light speed, you'd find that time aboard the ship passes much more slowly compared to time on Earth. This effect, called relativistic time dilation, has been verified through experiments with particles moving at high speeds in particle accelerators. Einstein's insight that space and time are interconnected revolutionized how we understand the universe. Instead of thinking of them as separate stages on which the events of the cosmos play out, we now know they form a dynamic, interwoven fabric that shapes everything from the path of a falling apple to the orbit of galaxies. Every step you take and every moment you live unfolds on this four-dimensional canvas, illustrating how deeply space-time governs our everyday existence, even if we don't consciously notice it. Quantum entanglement. Quantum entanglement is one of the most fascinating and perplexing phenomena in physics. It describes a situation where two or more particles become connected in such a way that the state of one particle is directly tied to the state of the other, regardless of the distance separating them. This connection is so profound that when you measure the properties of one particle, the properties of its entangled partner are instantaneously determined, no matter how far apart they are. This bizarre behavior has been famously described by Albert Einstein as spooky action at a distance, and it challenges our traditional understanding of how the universe operates. To appreciate entanglement, imagine a scenario involving two gloves, a right-hand glove and a left-hand glove. You put each glove into a separate box, seal the boxes, and send them to two different locations, one to New York and the other to Tokyo. If you open the box in New York and find the right-hand glove, you immediately know the box in Tokyo contains the left-hand glove. This seems straightforward because the gloves were predetermined to be a pair, and their identities were set before you opened the boxes. However, quantum entanglement is far stranger than this. In the quantum world, particles do not have predetermined states before measurement. Instead, they exist in a superposition, a combination of all possible states at once. When two particles become entangled, their superpositions become linked. For example, if you entangle two electrons, they might exist in a state where one is spinning up and the other is spinning down, but the specific configuration isn't determined until you measure one of them. When you measure the spin of one electron and find it spinning up, the other electron's spin instantly resolves to spinning down, no matter how far apart they are. What makes this phenomenon astonishing is its apparent defiance of locality, a principle suggesting that objects can only be influenced by their immediate surroundings. In classical physics, information transfer is limited by the speed of light, the universe's ultimate speed limit, yet in quantum entanglement, this communication between particles happens instantaneously, even if they are separated by vast distances. Experiments have confirmed this effect time and again, most famously in tests derived from Bell's theorem, which demonstrate that entangled particles behave in ways that classical physics cannot explain. To ground this in an everyday context, consider a modern application like quantum encryption. Quantum entanglement is used in developing ultra-secure communication systems. If two parties share a pair of entangled particles, any attempt by an eavesdropper to measure or intercept the state of one particle disrupts the entanglement, alerting the parties to the intrusion. This ensures the transmission of sensitive information is secure, something impossible with traditional encryption methods. Another intriguing potential application is quantum computing. Entangled particles, or qubits, enable quantum computers to perform computations at speeds unimaginable with classical computers. Entanglement allows qubits to process vast amounts of information simultaneously, paving the way for breakthroughs in fields ranging from medicine to artificial intelligence. In summary, quantum entanglement is a mind-bending phenomenon where particles are mysteriously connected in a way that defies the usual rules of space and time. Its implications stretch from reshaping our understanding of the universe to revolutionizing technology. Though it may seem abstract, its potential for practical use is vast and transformative, bridging the gap between the quantum and everyday worlds. Black holes. Black holes are among the most fascinating and mysterious phenomena in the universe. At their core, a black hole is a region in space where the force of gravity is so strong that nothing, not even light, can escape. This happens when a massive amount of matter is compressed into an incredibly small space, creating an object with immense density. To understand this in an everyday context, let's explore how black holes form, their effects, and some intriguing concepts surrounding them. Imagine a star much larger than our sun. Stars are massive balls of gas, primarily hydrogen and helium, undergoing nuclear fusion in their cores. This process releases energy, which pushes outward and balances the inward pull of gravity. Over time, a star exhausts its fuel. If the star is massive enough, it collapses under its own gravity when the outward pressure from fusion stops. This collapse can compress the star's core to a point of infinite density, called a singularity, surrounded by a boundary known as the event horizon. The event horizon marks the point of no return. Once something crosses it, escape becomes impossible. To visualize this, think of a trampoline with a heavy ball placed in the center. The ball creates a depression in the fabric, and any smaller objects, like marbles, placed near it, will roll toward the center. Now, imagine increasing the weight of the ball infinitely. This would stretch the trampoline so much that the fabric tears, forming a hole where anything nearby falls in and cannot climb back out. While this is a simplistic analogy, it captures the essence of a black hole's gravitational pull. Black holes are not cosmic vacuum cleaners that indiscriminately devour everything around them. If our sun were replaced by a black hole of the same mass, the Earth and other planets would continue orbiting it as usual, because the gravitational pull would remain unchanged at that distance. The key difference is that light and matter crossing the event horizon of a black hole cannot escape. One of the most mind-boggling features of black holes is their effect on time and space, a phenomenon predicted by Einstein's theory of general relativity. Near the event horizon, the intense gravity warps spacetime so severely that time appears to slow down relative to an outside observer. If you were to watch someone falling into a black hole, they would seem to slow down and freeze just before crossing the event horizon, never appearing to actually fall in. Meanwhile, to the person falling, time would feel normal, though they would experience an intense gravitational pull stretching their body, a process ominously called spaghettification. Black holes also play an essential role in shaping the universe. Supermassive black holes, millions to billions of times the mass of our sun, are found at the centers of most galaxies, including our own Milky Way. These colossal black holes influence the formation and motion of stars and can power quasars, extremely bright objects visible across vast cosmic distances. Despite their destructive reputation, black holes help regulate galaxy growth by consuming matter and releasing enormous energy in the form of radiation and jets. In the everyday context, black holes remind us of nature's extremes. They are regions where known physics breaks down, offering insights into questions about dark matter. Dark matter is one of the most mysterious and fascinating concepts in modern physics. To understand it, think of the universe as a vast, interconnected puzzle. Some pieces, like stars, planets, and galaxies, are visible and familiar to us. They make up what we call ordinary matter. But these visible pieces account for only about 5% of the universe. The rest of the puzzle is hidden, and a significant portion of this hidden part is something scientists call dark matter. At its core, dark matter is a form of matter that does not emit, absorb, or reflect light. Unlike the stars we see twinkling in the night sky, dark matter cannot be directly observed with telescopes or other instruments that rely on light or electromagnetic radiation. This makes it invisible in the conventional sense. However, we know it exists because of its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. To imagine this in everyday terms, think of wind. You can't see the wind directly, but you know it's there because you see its effects. Trees swaying, leaves scattering, or a kite soaring in the sky. Similarly, while we can't see dark matter, we observe its influence on galaxies and the universe. Without it, the behavior of galaxies and the movement of stars within them simply wouldn't make sense. For example, galaxies are collections of billions of stars bound together by gravity. If we calculate the gravitational pull based solely on the visible matter, such as stars and gas, the galaxies should fly apart. They simply don't have enough mass to hold themselves together at the speeds they're spinning. Yet, galaxies remain intact. The best explanation for this discrepancy is that there is a significant amount of unseen mass, dark matter, providing the necessary gravitational glue. Another striking piece of evidence for dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant objects, like a faraway galaxy, passes near a massive object, such as a galaxy cluster, the light gets bent, creating distorted or magnified images of the background object. The amount of bending depends on the mass of the intervening object. Observations reveal that the mass causing this bending is far greater than what we can see, strongly pointing to the presence of dark matter. To bring this idea closer to home, think about a flashlight beam cutting through fog. The beam lights up the tiny water droplets, making them visible. But imagine there's an enormous amount of something invisible, like air, moving with the fog. You can feel it and see how it affects the fog, but you can't directly see the air itself. That's analogous to how we detect dark matter. It shapes the fog of the universe, like galaxies and stars, but remains invisible to our instruments. Dark matter also plays a crucial role in the formation and evolution of the universe. In the early universe, it acted like scaffolding, helping ordinary matter clump together to form stars and galaxies. Without it, the universe as we know it might not exist. Despite all we've learned, the nature of dark matter remains one of the greatest unsolved mysteries in physics. It doesn't interact with light or other electromagnetic forces, and it barely interacts with ordinary matter. Scientists have proposed several candidates for what dark matter might be, including exotic particles like weakly interacting massive particles, WIMPs, or axions, but none have been definitively confirmed. In summary, dark matter is like the hidden framework of the universe, unseen yet essential. Its gravitational pull shapes galaxies, bends light, and helps explain the universe's structure. Even though we can't directly observe it, dark matter reveals itself through its influence, much like the wind reveals its presence by how it moves the world around us. Understanding it could unlock profound secrets about the cosmos and the fundamental nature of reality. Dark energy. Dark energy is one of the most mysterious and fascinating concepts in modern physics. It refers to a hypothetical force or energy that drives the accelerated expansion of the universe. To put it in perspective, scientists estimate that dark energy constitutes about 68% of the total energy in the cosmos, while dark matter and ordinary matter make up the remaining 27% and 5% respectively. It is dark energy that plays the dominant role in shaping the large-scale structure and future of the universe. To understand dark energy, consider the universe as a giant balloon. Imagine that this balloon is filled with dots representing galaxies. When you inflate the balloon, the dots move farther apart, much like galaxies do, as the universe expands. In the early stages of the universe, this expansion was thought to be slowing down due to gravity, much like how pulling a rubber band apart slows as the elastic tension resists. However, in the late 1990s, astronomers made a surprising discovery. The expansion of the universe isn't slowing down. Instead, it's speeding up. This observation, based on the study of distant exploding stars called supernovae, suggested that something mysterious was counteracting gravity and causing this accelerated expansion. Dark energy is the name given to this unknown phenomenon. It acts as a sort of anti-gravity, pushing galaxies apart rather than pulling them together. Unlike ordinary forces like wind or magnetism, dark energy doesn't seem to have a specific source. It permeates all of space and acts uniformly, like a force field that grows stronger as the universe expands. In everyday terms, imagine driving a car up a steep hill. Normally, gravity would slow you down, requiring you to use more fuel to keep moving. But now, imagine a mysterious energy suddenly appears, helping to push the car up the hill, even when you ease off the accelerator. This unexpected push is similar to how dark energy works on the scale of the universe. It accelerates the cosmic expansion, despite gravity's attempts to hold everything together. One of the simplest explanations for dark energy comes from Albert Einstein's concept of the cosmological constant. Einstein initially introduced this idea as a mathematical term in his equations to maintain a static universe, which was the prevailing belief at the time. Later, when it was discovered that the universe is expanding, Einstein discarded the cosmological constant, calling it his biggest blunder. However, with the discovery of accelerated expansion, the concept was revived and is now a leading explanation for dark energy. Dark energy can also be compared to inflation, the rapid expansion that occurred in the universe's first fractions of a second. Just as inflation caused space to stretch exponentially, dark energy seems to be causing space to expand at an ever-accelerating rate. The difference is that inflation occurred over an extremely brief period in the early universe, whereas dark energy operates on a much longer timescale. The implications of dark energy are profound. If it continues to drive the accelerated expansion of the universe, galaxies will grow farther apart, making the cosmos colder and emptier over billions of years, a scenario sometimes called the Big Freeze. Stars will burn out, and distant galaxies will recede beyond the observable horizon, leaving future civilizations with an increasingly desolate view of the universe. While dark energy remains a mystery, its discovery has reshaped our understanding of the cosmos. It highlights how much there is still to learn about the universe and our place within it. Scientists continue to explore this enigmatic force using telescopes, satellites, and experiments to uncover clues about its nature. The uncertainty principle. The uncertainty principle is one of the most fundamental and mind-bending concepts in quantum mechanics, introduced by the physicist Werner Heisenberg in 1927. It states that certain pairs of physical properties, like a particle's position and momentum, cannot both be precisely measured at the same time. The more accurately you try to measure one of these properties, the less accurately you can measure the other. This idea challenges our everyday intuition about how the world works, because in our macroscopic classical world, we can measure both position and velocity of an object, like a car, without any limitation. However, on the quantum scale, this is no longer true. To understand the uncertainty principle, imagine trying to measure the position and velocity of a tiny particle, such as an electron. If you focus on determining the electron's exact position by shining light on it, the light will interact with the electron and disturb its motion. The more light you use to illuminate it, the more you affect the electron's momentum, its velocity, and direction of travel. This disturbance makes it impossible to know both its precise position and momentum at the same time. The very act of measurement introduces uncertainty. This is not due to the limitations of our measuring instruments, but rather a fundamental property of quantum systems. The uncertainty isn't a flaw in our tools, but a natural consequence of the quantum world. Let's take a more relatable example. Consider a blurry photograph. When you focus your camera on a specific spot in the image to capture a sharper picture, the rest of the scene becomes blurry. In a similar way, if you focus too much on the precise location of a quantum particle, you lose information about its momentum, how fast it is moving, and in which direction. On the flip side, if you try to focus on its momentum, the particle's position becomes uncertain, just like the blurry parts of your photograph. In everyday life, the effects of the uncertainty principle are not noticeable because we don't deal with particles at the quantum scale. For example, when we observe a moving car, we can measure both its position and speed without any issue. This is because the car is made up of an incredibly large number of particles, and the uncertainty in their positions and momenta averages out. The uncertainty principle becomes significant only when dealing with very small particles, like electrons, atoms, or photons of light. This concept has profound implications for how we understand the behavior of particles at the quantum level. For example, in the case of electrons in an atom, the uncertainty principle means we can never know the exact path an electron takes around the nucleus. Instead, we describe its position in terms of probabilities, known as orbitals. These are regions in space where an electron is most likely to be found, but there's always a degree of uncertainty involved. You cannot pinpoint the electron's exact trajectory like a ball moving through space. Rather, you only know the likelihood of finding the electron in a particular region. Furthermore, the uncertainty principle is linked to the idea that nature at its smallest scale is inherently probabilistic rather than deterministic. In the classical world, we could predict the outcome of events with near certainty if we had enough information. For example, if we know the position and speed of a car, we can predict where it will be in the future. However, at the quantum level, things are different. The uncertainty in position and momentum means that even with complete knowledge of a system, we can only predict probabilities of future outcomes, not exact results. This uncertainty also has fascinating implications for our understanding of the universe. One such concept is quantum tunneling, where particles can tunnel through barriers that they classically shouldn't be able to pass. The uncertainty in the particle's position and momentum allows it to appear on the other side of a barrier without ever having the energy to overcome it in the traditional sense. In conclusion, the uncertainty principle highlights a key feature of the quantum world: the inherent limits of measurement and knowledge. It challenges our classical notions of determinism, where precise measurements lead to accurate predictions. Instead, it introduces a world where probabilities govern outcomes. And uncertainty is a fundamental characteristic of nature itself. This concept not only reshapes how we view particles, but also underscores the mystery and complexity of the quantum realm.